Okay. Hopefully you're managing to stay refreshed, you're eating the food that's out there. Someone's got to eat it, as my mother-in-law would say. Next up, we have a presentation from from some people who are actually building the stuff, right? So it's fine to listen to me, and it's awesome to listen to model providers, but let's listen to some people who are actually building practical applications for people in the real world. So please put your hands together and welcome my colleagues from the Generative AI Innovation Center. Thank you.
Hi, everyone. Good morning to you all. So I'm Meghana. I work as a machine learning engineer in the GenAI Innovation Center. This is, go ahead.
Yeah, hi everyone. My name is Vidya Sagar. I'm an applied science manager in Generative AI Innovation Center. Our goal was to work with large AWS strategic customers to build and bring their generative AI, to apply generative AI for their problems. So I have been with AWS almost for 7 years, and we have been in this space almost for 4 years, and specifically last 1.5 years, specifically focused on generative AI across machine learning, right? So as part of this journey, we have worked with more than 1,000 customers from Generative AI Innovation Center. We have a lot of ongoing projects with large AWS strategic customers where they are adopting generative AI for their production workloads. So the presentation, what you'll be seeing is primarily all our learnings and the solutions what we have put together, which have been in production rather than a prototype at various large AWS customers. So that's what we'll be walking you through, the technical stack, challenges, and how we solved it, applying generative AI for the production workloads.
Yeah. So we will be exploring the multimodal rack today. So this will be search across different modalities, which would be image, videos, and search. So let's go over the agenda for today. So we will be going over what was the motivation, and for achieving the motivation, what are the requirements that we need. We will quickly show you like a solution demo to first just show you, okay, how do things work, and then we can dive deep into, okay, what are all the components that went through building this demo, and then we will go over some use cases on the images and the videos, different modalities that we currently support, and then we will walk through the workflow and the architecture, like putting all these use case pieces together to build a holistic architecture framework for both the ingestion as well as the retrieval pipeline. And then we can end with some questions. So yeah, so motivation and requirements. So we want to improve. One of the main motivations for this was that we wanted to improve the search capabilities. Like we saw a lot of our customers were just using keyword-based search, or they were using semantic search without having a good metadata. So they never had great retrieval, and they wanted to harness the GenAI to improve their search experience. Then you want to stay ahead of your competition. Now that GenAI has blown up and everyone's using it, you want to stay ahead of everyone. So you want to make use of all the latest and the greatest models that are coming out today to stay ahead. And though there are so many different models and so many ways to build your services, you need a framework such that you can do continuous experimentation and to make sure that it's all unified in one place so that you can give it to someone to test it around and also to put it in production. Another important motivation driver was having a centralized platform that is scalable, and also it should be like a one-click deployment where you just deploy the framework and everything works out of the box as you expect. And you don't want to maintain different versions. It should be a centralized which has all your versions stored, and you can go back and go forward, and it's also backwards compatibility. So these were our motivation. And based off of that, we came up with the set of requirements for the search system that we are building. So the requirement number one, the modalities, what do we want to support? So we came up with video, images, and text. Then not just going off with the keywords, but we want to generate additional metadata on those modalities to make it more easier to search and also improve the evaluation system. So you need some context data. So for videos, you'll have transcripts if the videos have audio. You'll have different frames. And then you also want to generate some metadata at if the video has text, you want to make sure that you grab the text. If the video has some labels, like if it's about a nature, if it is about someone biking around, so you want to capture all these additional metadata. And then you also want to support some search queries like text to image, text to video, and image to image. So these are all some selections that you should be able to customize. So the next important requirement would be the indexing. How do we index, or where do we index rather? So the vector database is a very important choice we need to make. And here for our purpose, we were thinking some vector database that can support both your keyword search, support your semantic search, as well as a hybrid search where you can have like a weighted mechanism to retrieve results. Then we were going with the retrieval process, like I said, text to image, text to video, using different embeddings, different configurations for search. And a UI, because you also want to do qualitative evaluation so that the user gives you feedback directly saying thumbs up, thumbs down, or even give you like feedback saying, hey, this works well, hey, this is not working well. So, and then an infrastructure, and also making sure that some data science components are integrated through APIs so that you don't experience latency and see very good performance metrics. With these requirements in place, we want to quickly show you the solution demo that is going to capture all of this. So let's quickly look into this. So this one would be the text to image. But before we begin, we start with indexing on how to create indexes. So here we start. So this is a framework that we are providing where you can build your own index by selecting the different functionalities. Like what do you want to search for? Images? Okay. So I'm going to give you a S3 bucket link which has images. And here this is having this embeddings. These are all the metadata fields that we want to generate using these models. And then we generate that. Then we move to doing text to image search. So now you have the index, you need to define the search configuration, like what search do you want to do? Do you want to do image to image or text to image, given that image was the modality you selected? So here we're selecting text to image. Do you want to use a re-ranker? Do you want to use some embedding model? And then what are all the different retrieval types, like text, semantic, or hybrid? So once you define your configuration, here we are doing semantic search. So you do the search, and if you can see, it's actually very refined search where you're asking something like a person who is on a hike. It's very specific, and you're able to get. And here, this is just like someone holding a flower bouquet or a wedding bouquet, and you see all the wedding bouquet flowers. And then you have another which is like city skyline. So you're able to like retrieve all these different images of city skyline. And then we have one more example, which is like a sunset with bright colors. You're being very specific in some search terms where you see bright colors, and some which are like not that very specific, generalizable, like the city skyline where you see. This is an example of a hybrid search which uses like text and image. And here also we are being very specific, like someone on a hike or a person on a hike, and we see all these results. So this is text to image when you index an image. Let's go to the next one. So in the next one, we are doing text to video search. Here we do the same strategy. We first index, we create an index for the videos. It's the same UI page where you start with creating an index, you provide the S3 bucket where you have all your images stored, then you select what modality, so here it's going to be video. And once you have that, you want to know what all models or ML services that I need to generate additional metadata. Do I want to embed all the images that can be like retrieved from the video frames? So you select all these different configurations and you hit submit, and the indexing process starts. It's going to index in the vector DB. Next, you go with now, okay, let me see if my search works well. Can I retrieve it from there? So you again define your search configurations on what all re-ranker you want to support, what sort of retrieval you want to do. So here again, we'll try with hybrid first. Let's try with 0.5 for keyword and 0.5 for semantic. So then we hit search. So now let's start. So one thing to note here is here we are doing like a game, and we are just checking between two different teams. One thing to note is not all videos start at 0. They all start from the time frame where these matches were showing, to make sure that you avoid some advertisements which are not relevant to the data. So to be even more specific, let's say we take something like in the next example. This is like a video that we just want to quickly show. In the next example, we will go over something like a touchdown. So you just want to see the touchdown and you don't want to see the whole match. So here, if you see the second video, it's actually at that point where the touchdown happened, and we are able to retrieve at that specific frame instead of showing you the entire video to go find that frame. So this is text to video search. Next, we have image to image search. So here, same way, we create different indexes. Once we have all of that, you can directly go ahead and perform image to image search. So here, let me go speed up on this one. It's the same configuration that we create. And once we have it, you click on the search config and upload an image. So here you see it's a pathway with some like fall colors around. You want something that is very similar to this image or something that aligns with it. So you get the same similar image. You see the pathway, you see fall colors around. So same way, let's try for one more, like a bouquet of flowers. And you should be able to see like either someone holding a bouquet of flowers or just a bouquet of flowers as a decorative. And that's what we are able to see. So we are able to search from an image other images which are representative or adjacent to that image. So finally, once you have all these different search configurations built out, you definitely need a way to evaluate them. So we also provide a way to do like quantitative evaluation using some of the metrics that we have. So here, let's say you provide some ground truth data set, and the ground truth data set is also again in your S3 bucket, and now you want us to evaluate against your search configuration. So here you see it was evaluated against the two search configurations that are above, and we see that, okay, this is the precision, this is the recall, and this is how it's performing. So you're able to quickly evaluate also at the same time saying, oh, this configuration works well for this sort of setting, this does not work well. So this was the end-to-end architecture that we built for multimodal RAG. And now let's dive deeper to understand each of the use cases that was built, what all components went into building them, and so on. So we will start with the use case video. So now we want to know how did we do the video to text to video search and what all metadata was generated along with it. So to begin this, for our experimentation, we needed like a data set. So our data set consisted of some 500 videos, which were like around 20 seconds length, and these did not have audio. We also had 300 HD videos, and these were pretty long. So they were ranging between 20 to 160 minutes, and they did have like voiceover, like audio that we could also like use. And on a holistic level, all these data set was related to some TV shows or some vacations or some restaurant topics. So these were all the sort of labels that we currently had for this experimentation. Once you have the data set, you also need to define the metrics you want to use for this. For this evaluation, we used MRR. So MRR is like the mean reciprocal rank. So what the intuition behind MRR is that you want to make sure that in your retrieved results, your relevant result is at the top. And that's essentially what MRR calculates. So in the example that we have, let's say the user one enters a search term, and then you get 3 results, and only the third one is right. So it takes the reciprocal of that, because it's going to penalize and say that, hey, you did a bad job, you did not have the relevant result at the top, so you're going to get a lower score. So it's going to be 1/3. Whereas if you take the user number 2, he got 2 relevant results, but MRR only calculates the position of the first relevant result. So that is why it is 1/2. So the second was relevant, and the rank of the first relevant result was 2. So the score is going to be 1/2. For the third user, the very first result was relevant, so MRR score will be 1. And the reciprocal rank is going to be 1. And next, you're going to calculate like the mean of all the scores that you retrieved. So you can do it across users, you can do it across queries, and this is essentially what the MRR score represents, making sure that you have the relevant results at the top of your retrieved results. Next, we also went with like recall at top K. Because we had a ground truth data set, we wanted to make sure that all the relevant results are retrieved. But also know that it's at top K. You doing recall at a very large set, it should be possible that when you're doing like 100 retrievals, all the results are there, but you should always do it at top K to make sure how relevant are your results at like top 5 or top 10. So this is the metrics that we used. So once we had that, the next thing we had to go ahead was to build the metadata generation pipeline. So this pipeline is divided into 3 stages. The stage 1, where we actually run it against all this AWS ML services to generate metadata for the videos. Stage 2, where we actually kind of like group the metadata based on the video level as well as the shot level. So what is a shot? A shot is a set of video frames in a given video with the continuous action. To give you an example, let's say there is a video of a building. So that entire building till like 0 to 5 seconds would be one shot. And then from the building, let's say it moved to a park. So the moment it moves to a park, there is a scene transition. There is an action change. So that will be recorded as a shot number 2. So we were doing analysis at a shot level, at a video level. And then at stage 3 is where we do the actual embeddings, where we had 2 models from this is all available in Amazon. That is the Titan text model as well as the Titan multimodal model. So Titan text model embeds all text. Titan multimodal model can embed image, text, combination of image and text. And then we were using AWS open search service as our vector database to index all the metadata and the images. So once we have so now let's go a bit more in depth on the metadata generation pipeline. So stage 1 was to just generate metadata from all the videos. So these were the AWS services we used. Transcribe. If the video had audio, Transcribe will be able to retrieve that. Then recognition is also another service where you're able to generate metadata at the video level as well as a short level. So it had segment detection to detect segments in the video. It had label detection to give labels to the video. Something like, hey, this is about nature. Hey, this is about some fall colors. This is about a flower, a child. So you can also see some examples that we provided over there. So the first, at the top, we show the shot metadata. So it has timestamps to say from where to where is this shot in the video. Next, we are also showing label metadata. So here it's able to detect a child, accessories, handbags. So these are all different labels that Amazon has. I think there are over like 500 labels that the service can detect. Next, we have text detection. So the video did not have any text. So there was no text that was detected. Then we have celebrity detection. So no celebrity, so that was also empty. And then finally, face detection, where it's actually able to recognize a child and a person, and it's able to say, hey, their sentiment seems to be positive, their sentiment seems to be neutral, this is the predicted age group. Like, if this level depth of information is required, you can get it, or you can like stop at just getting the information that is needed. We also show the transcript of one of the videos that we were able to like process. And you get it at like a timestamp level of, hey, speaker 1 said this, speaker 2 said this, and it makes sure that it's able to identify that there are only 2 speakers and give you the dialogue based on each speaker. Then we have comprehend, which is like an NER, where you can detect different entities, detect sentiments, and also detect targeted sentiments, which is like, this entity was feeling this. So these were all the different, the first part, stage 1 was to just go over all of this. Next, in stage 2, now we wanted to segregate it between the shot level as well as at a video level. So then we started grouping all the metadata per shot. Like you see that is the shot metadata, which began at this to this index, and the index would indicate the timestamp. And this was all the metadata that was collected for that particular shot. So this was at a shot level. We also did it at a video level, where we sampled some shots to generate the video at a very huge level. Because that information is too big, I'm just giving you an example of how to do it at a short level. But we did it at both stages. And once we have the metadata generation, the stage 3 is supposed to be the embeddings. How do we generate embeddings? So we have 2 models, the Titan multimodal model. So here you create embeddings for images, embeddings for text, embeddings of images and text. So the first one, where we say embed images, the first one is just simple sampled middle frames of the shot, which is embedded. The second one in the embed image is actually embedding both the middle frame, the image, as well as the recognition text data. The third one is embedding both the frame as well as the transcribed text data. Same way with embedding text. So here there are no images used. It's only going to embed either the recognition data or the transcribed data or the comprehend data that we have. Then we also had like Titan text embeddings. So this is text only. So it's only going to embed the text, so images cannot be used in this case as we could in multimodal model. So that was at the shot level. Then we also did it at the video level. Here we sampled like 10 images across the entire video from the shots, and we generated metadata on top of it. So the same process using the two different models. So once we have that, then we finished all the indexing. Now it was time for retrieval and also to check how well we were doing. And we evaluated it against both the different data sets that we said. One was for the long videos and one was for the short videos, which did not have any transcribed data. So here, some of the takeaways were that the short level retrieval system outperforms the video level. So we were able to retrieve at the short at that particular time frame that we previously demoed. And we saw that the performance was much better at retrieval. So it's not highlighted, sorry, but it's like 93% as well as like 81% over the baseline performance. So there was a baseline, and we clearly see that adding semantics is much better than just doing like the keyword search. So these were some of our takeaways from this evaluation. And when we evaluated it on the smaller data set, which had like 20-second videos without any audio, we also saw pretty much similar results, but we saw that we did not need a combination of the image as well as the text, but just the image embeddings itself, there was like really good performance, like over 200% above the baseline. So even though we see this, it's always, we felt like because the data sets were a little different, it's always good to add a combination of text as well as image metadata, because the performance wasn't that off. It wasn't the best, but based on the data set, you can always pick and choose what sort of configuration you want to use for this. So not always relying on so quantitative can take you so far and saying that, hey, your system does good, but it always depends on what the end user perceives. So you always need like an A/B testing mechanism, a qualitative way to evaluate your results. So this was another framework that we built, where at the bottom, if you see, we have a voting mechanism to say, hey, method E is better, method F is better, or it's a tie. So this was like a qualitative way to actually get user input and to say, hey, this system is actually performing well. So based on our quantitative metrics, we narrowed it down to 3 approaches, E and F and G. So one was just transcribe. The other one was transcribe plus the multimodal images, embeddings. And G was a fusion of all the metadata that we had. And from the results on the user interactions, we could clearly see that the method G was way better. And we felt that the fusion of all the metadata along with the images was the best performing. So this was how we developed the whole video generation pipeline as well as the video retrieval pipeline. So next, I'll quickly go over how the use case for the images. So for the images, we use like an open source data set, which is the Unsplash data set. So this is more like the photographers have uploaded all their photos, and based on that, some photos have been downloaded by the user, some have not been, and this data set sort of gives you all that information. It also gives you information on what search term was used, what images were retrieved, as well as how many were downloaded. So this is what the Unsplash dataset provides you. There is a light version as well as a larger one. You can pick and choose. We use the full dataset. So how did we develop the evaluation dataset for this use case? So here you can see the first one, which says like the conversions table. So it tells you that for that given keyword which a user provided, was that photo ID downloaded or not downloaded? So it just gives you information on that. So based off of this, we came up with an evaluation dataset to use that keyword and also find how many times a particular image was downloaded when that keyword was used. So aggregating all of this, we came up with the ground truth, and for ground truth, at least one photo download should have happened. So that way we have like this night sky where these photo IDs were all downloaded. We had the frequency of how many times they were downloaded. We also have like the total frequency of all the downloads for that particular search keyword. So this information is what we were using as our evaluation data set for the system that we were building. So next, we divided the evaluation dataset into 3 tiers because the data was very skewed. We saw some which had like really high download frequencies, some which like very minimal, like in single digits. So we kind of like sampled the data into 3 tiers. But for today, we will just go over the tier 1, which has like most of the resources available. So once we have the evaluation data set, we want to know the metrics. So like before, we had the same top-end precision, top-end recall. We also had like a weighted recall because we had like how many downloads were possible. So this is like a relevance metric that is associated with the image. And we were able to like use that to calculate like top-end recall weighted. So this just gives information that how many of the retrieved results were actually present in the top N. And another metric which is very similar to the recall weighted but much more powerful would probably be the NDCG, which is the normalized discounted cumulative gain. So instead of looking at like the formula and what it means, the intuition behind this is that let's say you have retrieved results and it's in the format of 1, 3, and 2. 2 being it had like the most number of downloads compared to 3, which was above. So what NDCG gives you an idea is that an ideal situation would have been 1, 2, and 3, whereas your retrieval system gave you 1, 3, and 2. So the IDCG is what the ideal score would have been, opposed to the DCG is what your system is. So it's going to give you that value which is saying, hey, your system is off by so much. So that is essentially what the normalized discounted cumulative gain tells you, like how much gain is your retrieval system getting. So these were the evaluation metrics. And then we had the same thing. So we came up with all the different science experiments that we wanted to do. So you're more familiar now with all the indexing modalities and embeddings that we went over. So all the same text, different image embedding models. So here we introduced CLIP as well. And then the text embedding models as well as semantic indexing search. So OpenSearch provides k-nearest neighbor search with two sorts of distance measurements. One is the L2, which is your regular coordinate system distance. And the other one is the cosine similarity, which uses the dot product as of the orientations. So those were all the embedding spaces that we wanted to look into, like what we did previously. On top of that, we also wanted to explore some fusion, which is like a shallow fusion, which combines outputs from two separate retrievals, like just say keyword only and embedding only, and then combines them. And as well as the hybrid search, which is a capability provided by the OpenSearch service itself, where you can provide the weights, you can provide the sort of normalization you need to perform retrieval. And then we also wanted to explore different re-rankers over here. So we wanted to start with like something very naive, which is just based off of your keyword. Then we wanted to expand to use like a cross-encoder re-ranker. So whether cross-encoder is like where you can provide like a pair, like a query and a retrieved chunk, and then you're going to get a score which says, hey, is this relevant to this query or not? So this is what a cross-encoder does. It uses like a BERT model, and it has like two inputs that you can provide to it. So in cross-encoder, we explored two options. One was the MS Marco cross-encoder, which is like something that was pre-provided. And the other one was a fine-tuned BGE model. So we took a BGE cross-encoder and we tried to fine-tune it. And then we wanted to see how well it does on this data set. So once we have this, I just want to quickly go over the capabilities of the different searches that we provide. So for Fusion, it was just like, as I mentioned, this hybrid search. You can provide your normalization, so min-max normalization, where it's going to normalize the relevance scores. And then you can also provide the weights, which is 0.5 would be attributed to the first query that you provide. So it's a vector field 0.5. 0.5 for the next sort of retrieval you want to do, which is just keyword based. So this is how hybrid is configured in OpenSearch. Next, we have the fusion, the shallow fusion. So you have two different retrieved results. Then you normalize the ranking. Because there were only 5 results, we were able to calculate the diff as 0.2, and we were just ranking them based off of the retrieved ranks. Scoring them based on the retrieved ranks. And then we just added up to get the final on all the image IDs. And then you provide that as the new ranking system saying, previously it was ID1, ID2, ID3, but then after the fusion happened, the ranking order has changed. And then we also, this is how you do the the cross-encoder re-ranker. So OpenSearch provides you the MS Marco. So the one that is highlighted in gray is how you sort of deploy the model and get the model ID. And then you use that model ID in your search pipeline. It's the same thing as before, the whole hybrid search. In addition, you can also add this re-ranker and provide the model ID. And when you do the search, you also need to say that, hey, for this query, use the re-ranker. And you provide what all keywords need to be used for that re-ranker. So against the query, all these keywords will be, against these keywords, your retrieved chunks would be evaluated to see the final score, and then the ordering would then be updated. And then we also used a BGE cross-encoder. So this was at a very high level how we trained the model. So we took like 3,000 samples from our existing Unsplash data set itself. Here you need to create query, positive and negative pairs. So the positive would just be everything that is in the ground truth or that conforms to the query. And negative needs to be a hard negative where it should never be retrieved for that. The query should always give you like -1 when that particular negative chunk is being retrieved. So it needs to be hard negative. So this was the pairing that we created. And the training process was simple. We used SageMaker to perform the training. So the training group had one positive, that is query, and a positive example. And then we had query and negative examples, which was provided in for. So this is like some of the standard training processes that is being used to fine-tune a BGE cross-encoder model. So once we have that done, this is all the connectors that I just wanted to quickly show you how to do it with OpenSearch. You deploy the model in SageMaker, you create a ranking connector with it, and then you create the same process as uploading the connector to get the model ID, provide the model ID in the search pipeline, and then in the search body, you just add that additional information of, hey, use this re-ranker. This is the query text that you need to evaluate the chunks on. So you provide all this information, and this is all the setup. So next, we will go over the actual experiment results that we got. So first, we just wanted to evaluate it on just the embedding space. I hope the table is visible. We ran a lot of experiments I've cut down, and these are like some of the important experiments I wanted to highlight. So all those values that have been highlighted, they were like the highest. And we mainly used NDCG metric because we had the relevance scores available. So we did something like top 50 as well as top 10. And what we saw was just using text-only keyword for evaluation gave us really high score. And also using like clip embedding model with both the L2 as well as the cosine similarity gave us like the highest. So the other keyword-based retrieval wasn't great, as well as it was better, but it was not as good as the image embedding. So the quick takeaways from here was that keyword was better than using even the Sonnet generated. So Sonnet is also another LLM from Anthropic Claude. So that the keywords that were generated by that model for the images did not give us like great performance. Just using the keywords from the Unsplash dataset gave us like the best performance. But when we compared it with semantic retrieval, Clip gave us like better results compared to the other embedding models that we used. And so among the two different modalities, semantic outperformed the keyword-based retrieval. So quick error analysis that we also wanted to do was we saw that the ground truth data set was not very exhaustive. So the image that in one of our results, say for nature, we were able to retrieve these 5 images. But as you can see in the ground truth, only the 3rd image was there, but the other 4 images are still relevant towards nature. So we saw that the data set was not, the evaluation set or the ground truth that we were generating was not that exhaustive, and there were no clear distinctions between the different images that we have retrieved. So this was one thing that we observed. And so what we concluded from that observation was that we were only going to get the lower bound, and this is not going to be the upper bound because the data set is not very conforming. So next, we wanted to apply fusion as well as the hybrid techniques. So here, when we did it, we saw that the hybrid search performed better than the shallow as well as just using single modality like keyword or semantic. So hybrid search was performing well, and the weights for which it performed well was 0.5 and 0.5. So this was the second set of experiments that we did, now trying with fusion. The next set of experiments that we did was using the re-ranker. On top of the hybrid, we added another layer of re-ranker to see if it affects the relevancy scores or relevancy order of the results. And what we saw was all the re-rankers did not, they all failed to improve the NDCG from the baseline hybrid search that we had. So we were like, we wanted to do some error analysis on why this was happening. So it was the same thing. And also, why didn't the fine-tuning not work? So you would expect the fine-tuning to work, because on the training set, we saw that it performed really well. Why did it not do that? One of the reasons was it was overfitting. And why did it overfit? Because our hard negative examples wasn't very distinguishing from the positive. So it was like very similar. Like I showed you the nature example, those 4 images could easily be referred to as nature. But because it was labeled as something else, it was using that label, it was not able to like make a hard distinction between the queries and the retrieved chunks. So it kind of like confuses the model. And because you try to get better metrics during training, you run it for more number of epochs, and this essentially results in overfitting. And this is what we observed with our fine-tuned model. So. And also one of the reasons why we saw the re-ranker wasn't doing that great was, again, the labels were not exhaustive. Like the ground truth should have contained those images as well, but they were just being tagged as trees, which is very misleading, and it should be more specific and oriented towards the images that were there. So that was one of the things that we observed. So we were calling all these metrics as a lower bound for the given data set. So next, I'll quickly go over. So now that we have the 2 use cases done, we wanted to build everything into a single workflow and architecture. So this was the main idea. We wanted it to be a quick experimentation platform. We wanted it to make sure that it's scalable, enhancing the user experience by making sure we get qualitative feedback as well, and also improve the business operations. And so we came up with this architecture. So this is the architecture where the bottom half is essentially the ingestion pipeline. So we use step functions, we use AppSync, which is going to be like the APIs targeted. We also have like lambdas that were built in to do the retrieval system, as well as lambdas to do the evaluation system. So this is like the end-to-end architecture. A bit more dive deep into the ingestion, like the supported modalities. Let me go a little in the interest of time. So this was the idea behind the ingestion. You can provide what all configurations you want. Hey, I want this model, I want this keyword, I want this metadata to be generated using recognition. So you provide that search configuration, and essentially the step function will get kicked off. So here you can see one is for the image, one is for videos, and the other one is just to make sure that the pipeline is running. So it's like a monitoring service that we have built. So you have different pipelines running based on your search configuration that you have. And this is for the image. So once image pipeline is kicked off, it uses all these services that we spoke about, like Claude, it uses recognition, it uses transcribe, and for images, Claude, Lava, as well as the recognition to generate the metadata. For video, it uses the transcribe, the recognition, as well as Claude to generate additional metadata. And then once the ingestion is done, so for ingestion in the metadata, we have different options. We provide Lava as well as Bedrock Claude. And this is like the prompt that we are using to generate metadata for the model. So we have different, so in the prompt, it's always good to be as explicit as possible. So we have like things like use this as description, use these colors, detect objects, detect the style. And this is what the model is going to use as a template to detect. And then we also have other options like recognition, SageMaker endpoint that we spoke about earlier as well. And once we have that, this is like the image metadata, a sample. So you have text, you have the keywords that were retrieved, the style and the colors. So all of this was given to us by the Claude model. So that was the metadata generation. So next we'll quickly go over the retrieval pipeline. So we saw the different retrievals that we perform. For images, it is pretty similar. Like you have a query expansion phase. Then you have like what sort of, using OpenSearch, whether you want to do keyword, semantic, or a hybrid. And then you also have the option of adding a re-ranker or a post re-ranker. So this is the text to image or text to video pipeline. But for image search pipeline, we have like two. One is to just do the similar search where you would have images and then you can just semantically like embed it and then in the semantic space find relevant images for it. Another way would be to generate additional metadata. So this way you get like for example, if you're looking for something like a mortgage, it should also be able to give you something like, hey, home improvement projects or something like that. So this is the adjacent search that we also wanted to propose, and we kind of use like Claude model to find all these additional keywords to it. So some of the next steps, so this is essentially the entire model. And some of the next steps that we want to do is add a feedback. So the qualitative, a thumbs up, thumbs down. We already have the evaluation system that we demoed, but we also wanted to have a way to give feedback. We also wanted to like provide more custom model support for the OpenSearch re-ranker. We just currently have the BGE. And we also wanted to support conversation where using the context from the previous message, it's able to like retrieve more, like storing your chat history. So these are all the next steps. And please do reach out to the GenAI team. So this was the team that built this entire model. So it was me, Anila, and I have Vidya over here. And yeah, please do reach out to us for any use cases or concerns that you might have. Yeah, thank you. Yeah, we have like 5 minutes. We can take some questions.
Can I ask the first question? Because I'm going to preempt a number of questions here. Those slides were super dense with awesome information. Can you share the slide deck for us, please?
Yeah, I think we should be able to share the slide deck. The way is I think we'll figure it out either through LinkedIn, I think, or yeah.
So follow you guys on LinkedIn is probably a good way of doing it, and
yes,
you'll be able to make it available there. I look forward to it. Thank you.
Thank you.
Yeah, go ahead.
Excuse me. So you were showing the ingestion, a couple of questions. So you were showing the ingestion pipeline, like how much time it took for doing all these ingestions?
So yeah, it's like an experimental process. So once you have the pipeline set up, and then I think the main thing goes over experimentation. So the more experiments you do, you will realize what is the gap that you're missing, and also performing error analysis. So it's definitely like months of effort, but yeah, we would we can definitely like speed it up now with this in place.
I think just want to reiterate, right? The way it works was, I mean, you can have a default configurations up and running within less than a week. But at the end of the day, I think as you can see, it's primarily coming from the science side of things, where you want a well-defined system and everything. So from our past experiences, as we already have a base frameworks and everything, so it's pretty fast. Right, to onboard your existing stuff and look at the performance stuff. So yeah, that's how it is. It will evolve.
Okay. How is your inference so much faster? For example, I mean, you are showing in videos, so we don't know like really like what is happening behind the scenes.
Yeah, that's all real time. So yeah, our inference is quick because of some of the services that we have used. So we have used AWS AppSync, which is providing you the API where you can like query, update. It also provides you subscriptions, which you can quickly like get results to in during conversation fields. And we are also using Lambda, which is like another serverless, so it can scale as the number of requests come in. And all the models that we have, they like OpenSearch has like super low latency with retrieval. It's in like less than milliseconds, to be honest. So that also helps up with all the speeding processes.
Okay. How do you compare your OpenSearch retrieval time compared to the Elasticsearch clusters that we have?
We haven't done a comparative evaluation on that, but yeah, we can definitely look into that. Because it was doing a great job, we didn't try to explore others, and it was also providing out-of-the-box features of supporting hybrid and re-ranker support, so we just went with it.
I think the main thing we always look out as we work with our customers was how can they scale efficiently and everything. So that's why we prefer a lot of managed solutions out there, which AWS offers out of the box. So that's why I think all the solutions what we see is primarily a managed solution rather than a custom homegrown managed solutions, right? So that's why I think throughout our solutions, we always recommend Amazon OpenSearch, which has been in production for a lot of customers out there for large volumes of data. And just to highlight over here was the video example, what you see, we have a public reference, which is a blog. For Veriton, we are able to onboard this solution, and they are able to bring the terabytes of data onto that so that they can augment this generative AI-based searches very efficiently for their videos. So this is a publicly referenceable solution at this point.
Got it. What is the context length that this could support? Like, I mean, you were showing
So
like
for
small
Claude,
searches.
yeah, for Claude, it's like around 200,000 tokens, but we don't use 200,000. It's like in hundreds, I would say.
Got it. And what is the size of these machines that you are using?
Size.
For example, like the P4D.24x large, like whatever it is. Like, I mean,
It's I'm not too sure on the configuration, but for that they're only used mainly if you want to fine tune a particular model. They will have like around 64 CPUs or maybe one GPU, I guess. But yeah, it's only for a fine tuning use case. And once you have fine tuned and you want to support an endpoint, SageMaker can be quickly used to deploy that endpoint.
wanted to understand because like how much cost implication that
So the one that we used wasn't a huge model, so I can't remember it on top of my head, but it did not incur a lot of cost for support.
Two questions. One, if you can share again your emails and the name of your project in hiding face. And the second, if you are planning to include sound identification, sound classification in the video. For example, the shot of a ball in a racquetball, that kind of things.
Yeah, we can definitely do that for like video-based retrieval. We were able to for sports, we were able to retrieve like something like a touchdown happening. And another example is like, let's say there's a customer who has who's into like all these televising cooking shows. You can exactly go to that frame in the search where they're actually preparing like a grilled cheese sandwich. So you skip all the other parts where they're talking or they're introducing or something, you quickly go there. We do have that support for doing timestamp based retrieval.
I think the basic thing we want to highlight over here was, I mean, we are showing our own solution, but what we want to highlight was AWS has all the components available on the system, so it's easily plug and play at this point for you. That's what our main goal to demonstrate over here was. Yeah.
Go ahead.
So one question: do you also parse the PDF files and like bring the images out of them, or no? Just image and a standalone?
No, we are able to do that. So there are a couple of libraries that are available where you can just get the text component and the image component, and once you detect the blocks, you can take the image block and pass it to like an LLM to get your additional metadata.
Got it. Thank you.
Oh, yeah.
Yeah, so that was a lot, and I'm sure it's from a developer's point of view. So I'm looking at this, and we are in one of the spaces we're in is digital marketing, and I see this highly applicable to all the prompts and everything you have here. Similar, like for example, we use CapCut, and from a user point of view, everything you have here is literally in that application, for example. But I suppose the Amazon version is more for an enterprise-wide, if you want to have larger and larger images and so forth. But I think for podcasting and general digital marketing stuff, it's really applicable. You agree?
Yeah.
I think what we have seen was just, I mean, we can't name the, I think we can for a large customers who have a lot of domains and everything, when they have a lot of marketing images and everything, if they want to identify what are the relevant images, they have a concept idea somewhere they saw in the web from their internal repository, it can surface up that so that it can provide the recommendations. What you see here is a search, which we can power with essentially with the personalized recommendations, where you can do text to image searches to recommend. I mean, let's say you're creating, I want to create, some new commercial came or some new template you had to create. You can essentially go and look into your entire repository. The main thing we want to highlight over here is this is primarily for the enterprise data. When you already have the data, it's easy to drop in your data into the system, and you have a text to image search system out of the box.
Yeah, also, if you are, again, in the digital marketing
Yes.
business, there will be a repository of data that you could use across customers, right?
Yes.
And this kind of model works. Okay,
Yes.
great. Thank you.
Okay.
I have a 2-point question. So for a PDF that has text and images, have you ever solved those use cases? How do you ingest that data? And if you have, what kind of embedding approach have you used for a combination of text and images? When a user has like an ability to ask questions specifically for the image, or they want output of a text and image together, something like that.
Yeah, so for addressing the first question where a PDF has images as well as text, so we also use textract, which can like parse, if you have like a structured data like tables and all of that, you can quickly use textract because it's able to extract all the table and all that specific data. There are like additional Python libraries also like PDF, DM, I think what I remember, which can also like extract images from the PDFs as well along with the text. So you can use a combination of these two to get your text blocks as well as your image blocks. And to embed them, we use the multimodal model. So Amazon provides the Titan multimodal, which kind of like performed really well for us in our video use case. So there you can embed not just images alone, you can have image plus text embeddings as well. So you give this to the multimodal, you provide this as input, your image in base64 encoding as well as your text, and it returns you back an embedding which you can like index in your vector database.
Have you also used, like, if you, after your KNN results, have you directly passed the result of the image and text together to the model? And is it able to use that to give a correct answer?
Yes.
Has that approach worked for you?
We have mainly dealt with text to image, text to video, and just image to image. But that should also be possible because you can still embed the given text and image that is used as input using any embedding model. And then you can use that for like searching using semantic search. And then you can also do another way where we also generated additional metadata from the keywords and the text and the image itself and use that to also do the retrieval.
Is there a limit on the amount of tokens that you can pass on the Titan model?
I think yes, it is 8096, I think.
Okay. Thank you.
Yeah, I think just want to highlight, I think in the earlier session, someone is asking about the tables and everything as well. So we had essentially benchmarked that with the tables, text, images and everything. And I would recommend just out of the box, I mean, we are not demonstrating over here. We have Amazon knowledge bases, Bedrock knowledge bases, which will support it out of the box. You can just drop in your files over there and you can look at the performance. And under the hood, it will be using the same solutions, but again, it's a managed solution. You don't have to look at the underpinnings and it can provide you what the best performing retrieval mechanism across.
Hello. So I was wondering if this is part of an actual research paper or is it like a blog post that's going to be posted?
I think there are multiple blog posts over here. One blog, I mean, as you can see, the text to video one, it has been published earlier this year, along with our customer Veriton, where we have augmented generative AI based search for their video repository.
Okay.
And the image to image one, I think there are upcoming blog posts in this space. And as you can see, again, we did it on a certain data set, but again, these results are applicable for different enterprises over here. So that's why we are just showing what are the approaches and the frameworks which you can leverage for your enterprise data to, by default, it will offer you the search, but it might not be well refined for your enterprise data where you have to fine tune it further.
I was also wondering like on the orchestration of like, you're like combining the outputs of like AWS recognition, transcribe, comprehend, or something. Like, can you, like, does the blog post cover a little bit more about like how the code orchestration works, how you format multiple outputs into one output and then feed it into another input?
Yeah.
And then input it
Yeah, we do have that same stage kind of like walkthrough in the blog post as well.
Yeah, that's cool.
Yeah, the blog post was published, and I think we will try to push up. Please ping us, so we are happy to share. It's on AWS machine learning called how Veriton has enhanced their search pipeline. So,
what is the vector DB called? Product is
Amazon OpenSearch is what we use.
OpenSearch is the one. Okay.
Yeah.
Thank you.
Thank you. Question I have is, what happens if you just embed the image directly into the vector DB? Does it go like in one set of coordinates totally separate from the text labels?
No, so we did that and it's actually in the same embedding space, the image as well as the text. That's what we saw when we did our video use cases.
Okay. Thanks.
Thanks. In case of situation, you have a database, let's say, of merchandise, a series of products and so on. And we know a lot of those things, they're no longer are sold for whatever reason, they're out of the cycle, right? How does that impact the workflow? How do you remove labeled products, et cetera, and be able to maintain, the coherency as well as the accuracy that you're talking about?
Because most of the steps, what you see in the ingestion is a pre-processing step. It's not a real time, right? It's a pre-processing step. So whenever you want to remove the images, you can just again pass through. I mean, what we are showing is how to ingest. We didn't demonstrate how to remove, but again, you can do the pre-computations of those embeddings, and you can essentially remove from the vector DB for the old images which are not relevant anymore. As you said, one of the ways what we have seen customers have been doing was after you get the results out, you can do a post-processing step, cross-checking against your existing databases and filter out the results, what you want to present to the external customers. You can essentially add a post-processing after the results are retrieved. We are doing re-ranking right now, but we have seen various customers using their existing business logics or some kind of mechanisms to identify which ones needs to be shown to the external customers.
Okay.
Hi. I'm curious if you're able to customize the ranking for each searcher, so like based on their previous queries or like based on their previous like selection. Are you able to like input that for every different searcher?
Yeah, I think that's what is primarily called hyper-personalization aspects of things, where Amazon has Amazon personalized. That's what we're working with a lot of e-commerce customers right now out there. Similar to the answer, instead of passing the post-processing to a re-ranker, which is a keyword or something, you can pass it through a personalizer, like services like personalize, AWS personalize, where you can pass your past context on the results, which can re-rank for you.
Okay, so part of the post-processing.
Part of the post-processing. That's again next in the pipeline when it comes out.
Awesome questions. I think we'll just go for one last question.
Okay.
And then I think lunch is very close by. So,
thank you. So, is it fair to say, according to your experiments, that cosine similarity is the go-to metric for all the modalities? Or do you think there are any use cases where L2 norm Euclidean is more performant and more accurate?
So overall, we usually use cosine similarity, and like I can give you an example. Like in a coordinate system, if you take like an equilateral triangle, like L2 will return the same distance between all, whereas if you take the cosine similarity, it's based on the angle and the orientation. So you might actually get something that is more similar in nature. I mean, you can use any one based on the case, but cosine similarity is like the most preferred choice in, whenever you're doing KNN and all that.
I think I would say always map back from your business metric to what results in. So that's what we have always seen in standard in any GenAI systems right now out there. The metrics will map back into, there are a lot of metrics out there, as you can see. It always map back from what exact business metric you're looking for your specific business use case, because every business use case differs, right? So.
Yeah, I mean, according to your experiments, maybe you had some cases where L2 or L1 norm would be more performant. Yeah, thank you.
Okay. Thank you so much. This has been a fantastic session. It's been really awesome to see. Everybody, please put your hands together for Generative AI Innovation Center. So I think we'll call that a wrap for this morning's program. Please do come back here for 2 o'clock. Lunch, I'm told, is not far away. So if you've got more questions, then continue to have our conversations in this room. Lunch is through beyond reception. You know where it's at. And I'll see you back at 2. Thank you.